Hello and welcome. This is a video about computer programming, so if that is not your bag, you should probably leave now. Yet another bloody framework. Part 1, the data framework, history and evolution. This video is partly for the UK dev group, as I never got around to doing it as a presentation. If it has escaped into the wild, then this is about a data framework development using Pascal, although the same thing would work in any proper programming language. A couple of years ago I started rewriting my data framework. The version I had was a partial extension of something that had been created in a hurry, and I had never been happy with it. This and subsequent videos are intended to show the process as it has evolved and is still evolving. This initial video is a brief summary of the things I considered and the decisions I made in getting the core data framework to where it currently is. I will start with a brief history, followed by a short account of what I have done, and then I will look at some code and how it works. The second video is intended to show the data framework in action, and the other two videos currently planned will hopefully show the rest of the framework. That is the current plan, but anything may happen between now and then. The intention is to keep the videos to about half an hour. History. Just humour me. I have written COBOL as a job, and I have used Turbo Pascal for fun in the days before Delphi. I started with Delphi version 1 as part of my job when it came out, running on Windows 3. I bought Delphi 7 Architect in 2002 to get the Bold MDA add-on bundled with it. I tried Bold for a bit, but it never quite worked. I do, however, still like the idea of MDA, and there are active MDA-based development systems available for anyone interested. I then became a fan of client datasets for a couple of years, in conjunction with the ball and socket server for three-tier development on internal networks. The first version of my framework was a wrapper around the T-client dataset. This started around 2004 or 5, and my first attempt at code generators stems from this activity. I ceased being a fan of client datasets when I used one in a situation where it failed catastrophically within 5 minutes, which was extremely inconvenient. The requirement was for it to run 24/7, but it never lasted more than 5 minutes, typically failing within 3. Following that failure, I only used client datasets for lookup lists, and I no longer even use them for that. I view memtables that are also descendants of T-dataset in the same way. In my code, I do not use any T-dataset derivative in the client these days. To get around the failure, I hurriedly built the first version of an object or ORM framework. This was probably around 2010. It was primitive but worked well enough. I updated it around 2011 or 12, but it was never a complete system, and I started on version 3 in 2019. This was still an object framework, but with a more complicated object structure. This version never went beyond an early stage. This was followed with version 4, which was a reversion to a T-dataset lookalike, based on the T-list to hold data records. Well, to be honest, all of the versions after version 1 used T-list or T-object list to hold the data objects or records. It has now morphed into version 4b, where the T-list has been replaced with a double linked list. The indexes are still T-list based though. There are two other ghosts that affect my development strategies. Firstly, as I wrote COBOL for a while, say no more. The other legacy issue relates to databases, specifically relational DBs, as I trained as an Oracle DBA around 20 to 25 years ago and bought into the Oracle view of data and databases. I'm going to concentrate on the current version 4b, as the older versions are discontinued, mostly. The data object from version 3 has become the header for version 4, so I will cover that bit, and the indexing from version 4 is continued into version 4b, although the data structure itself has changed. I will start with my development rules. It's my system, so I can apply my rules without inconveniencing anyone, at this point anyway. Objects either contain data or do processing, but never both. This is a bit restrictive and sometimes it makes things appear a bit artificial, but there you go. A data object can have getters and setters, but that is it. Where the object is a list of other data objects, their methods to search for and find data objects are counted as getters. As this video is about data sets or data object lists, just using data objects, there should be no processing going on anyway. As a general rule, I do not do solid. This is because I use virtual and override methods in class hierarchies, and this breaks the solid rules. Some people take this as an extreme view, but I see it clearly stated in plain English in the rules about solid. And I like short names for variables and methods. Yes, I know, get over it. So a quick look at version 3 of the framework, which never went beyond a bit of testing, but has been partly carried over into the current version. This is a logical view of a rather over-complex object list arrangement. In a standard class or object, we have a bunch of properties with their types. Name as a string, status as an integer, that kind of thing. But we know nothing about any constraints that may apply to them. What I want is to define a property as being a type string. It is required, so it's not nullable, and the length should be between 4 and 16 characters. To achieve this, I defined a data property class. This class then has all of these things that I want to know about an object property, including the actual value. The data object is then a list of these data property objects, and a data list, or an object list, is a list of data object lists. Confused? You will be. Should there be a single data property type with the value as either a string or a variant, or should it subclass the base data property for each required data type? I've tried both and it really does not make much difference. Here you can see the derived class format starting with the base class. Most classes have validators, although a Boolean property does not need one, but the date property has a date validator, and the currency property has a currency validator, and so on. And here we have the data property list, which corresponds to the data object as the list of data properties. And then we get another list of data object lists, and this corresponds essentially to the data set, to the object list. This worked, but it's a bit of a memory hog. For example, consider a data object with 10 properties, each of which has a validator. A list of 1,000 data objects could then contain 10,000 property objects and 10,000 validators. And here's the validator. It's a simple thing that just checks the supplied value against one or more reference values. Building the validator into the data framework means that it can be applied automatically at any point. This does work, but it's a bit OTT for an object framework. Moving on, I think of version 4 both subversions, as a dataset rather than an object list. Although both types are lists of objects underneath, the distinction is a bit nebulous. An object list, at least the way I did it in my ORM versions, is a list of objects. The container itself does not really matter, but I used a T-list or a T-object list. The data objects are then typical descendants of T-object, with properties like name as a string, ID as an integer, etc. In my ORM at least, each dataset contained different object types, so a customer object was different from a sales object or a stock object. Other ORM frameworks may be constructed differently. In the dataset, the data object is generally referred to as a record and does not need to contain information about the data type. That information is held in a header and applies to the entire dataset. The data record is just an array of values, or at least it can be that simple. An array of strings or an array of variants, perhaps. In T-dataset and its descendants, the header is the T-field defs. In mine, the header is a single data object from version 3 of my ORM, which we looked at a minute ago. This way, I only create one validator per field if validation is required. I call my dataset a data list to distinguish it from T-dataset, which it most definitely is not. Am I just reinventing the wheel again? Possibly. But consider this view of wheels. Wheels are all designed to go round, but they are intended for different environments, conditions and loads. There is no common wheel that does everything. A couple more design considerations. At the time I was starting this, I was planning to use 3-tier and REST as the standard way of handling applications. 3-tier is my preferred format, but I had not previously used REST as the communication model. On the server, a query component gets data from the database. This is converted to JSON and returned in the HTTP response. I only want the actual data, not the header information as well. And note that with FireDAC in Delphi, you can get it either way depending on how you tell it to produce the JSON. In this general case, my data list has no place on the server and T-dataset has no place in the client. I use JSON as the transfer medium, but it could equally have been XML. Both are simply formats devised to enable data transfer as text and are best used in that context. Either way, I do not want any intelligence or metadata in the transfer, just the values. If the endpoint has been defined correctly, it will always produce the correct output in the format that has been published. And if the client has been built correctly, it will be designed to handle the data in the expected format. Yes, quite possibly too many ifs in that last statement, but that is the way REST APIs are supposed to work. So, it is expected that all data will arrive as strings. An HTTP response is a string and all JSON and XML are strings. The traditional thing to do then is to convert some of the received strings into other data formats like numbers and dates. But why do that? If the data is going to be displayed, it will be displayed as strings. When a number is written to a controls canvas, it is converted to a string. If you do not believe me, look at the VCL code. So, when is a number not a string? The answer here is when it is used in either a calculation or a comparison. In a read-only situation like a report, it never needs to be anything other than a string. It is simply not a requirement at any point to convert the value to a number on the client. As a consequence, the data records for version 4 of my data framework are just arrays of string. The last thing to say at this point is, as I have posted a number of times in the group Slack channel, I am trying to write code that works in VCL, LCL and WebCore. The lowest common denominator is obviously WebCore, so nothing fancy, which really means nothing newish like inline vars. Just very plain, traditional Pascal. Such code should also compile in Oxygene, although I'm not currently testing that. Generics is a case in point, having been implemented differently in Delphi, FPC and Oxygene, so cross-framework code really does need to be completely devoid of generics. Does this matter? No, not at all. And now for a brief intermission. So, yet another bloody framework. Version 4b. What does it look like? Well, having built version 4 around the T-list and got it all working, I then thought to myself that as I had never built a double linked list, perhaps I should try a version of the framework around that, rather than the T-list. If I had done this presentation or video a couple of years ago, I would have shown the T-list based version, not the linked list version. To be honest, I still do not know which is better. I do know that it is dragged on for over a year. I do not work on it full time, obviously, just a little bit now and again. I hoped initially I would just have to change a few methods, but in the end it was a complete rewrite of the data list. Is there any real difference? I do not know. T-list is a wrapper around an array of pointer, with a few methods to add, move and find. You can jump to any point because it's an array, but it has no concept of next or previous. If you are looking at item 563 and you want to go to the next item, well, you add 1 to the current position and go to item 564. On the other hand, with a linked list, it cannot just jump to item 187 because it has no idea where that is, unless it counts through from the start. However, it can just move to the next or previous nodes. Essentially, it is a case of swings and roundabouts. All design decisions are trade-offs. If you want to find something, you have to look. T-list has an index of function, but this just starts at the beginning and works through to the end, stopping if it finds what it's searching for. A start to end search in a linked list is exactly the same item by item check. The only difference is how it gets to the next item. The indexing in my list is still list based and has not changed much at all, fortunately. Anyway, having created the linked list version, that is what I am now using and what I'm going to show. The thing you can see here is the ER or class definitions for version 4b. The outer shaded areas denote units, so some units contain one class and others 2 or more. A problem with diagramming is that it needs to be kept up to date, and that is often a low priority operation. But this was correct at the time the video was recorded. While I am a fan of modelling, I do it my way and use whatever I think suits the task in hand. I generally use ER, SSADM and UML, and I am quite happy to mix them up in one model. The associations shown are either ISA, which means it's a descendant class, or a HASA, which means it contains an object of this type. All pretty standard stuff, really. The data stuff is in the middle column, starting at the top with the node record and finishing with a list of data lists, which is sort of like a .NET dataset. The stuff in the left column has validators, carried over from version 3, as are the property definitions as field defs, and the properties list as the data headers. The list links at the bottom hold associations between single data lists or datasets. On the right there are endpoints, which hold details of exactly that, change values used for changes and undo handling, and at the bottom are the index processes. I am not going to bother looking at anything in the left-hand side again, so I will start at the top of the data structures in the centre of the model. I did start with a node object, which then contained a data record as an array of string. This was the existing record definition from version 4a, the list-based version. I then decided that was unnecessary, so changed it into a single node record object, or class if you want to be picky. It has a double linked list, so it has two node pointers, one pointing forward and the other backwards. Simple stuff really. Okay, I gave in and added a record ID, which is an integer. This could be an ID, an index or anything else really, but is not a required value. It also has a status flag, which we will see more about in the next video. The records are contained in a double linked list, which really is nothing other than a chain of records. As I have said before, the interface section should tell you what everything is or is going to do, so there is one label for each property and each method. The find methods, that is the methods with the fnd prefix, are methods to do just that. There are some list methods, node handling methods and node finding methods. And a couple of properties. Looking down at the methods, there should again be a label, which may often just be a repeat of the interface label. Uncle Bob, that is Bob Martin, says that every comment is a failure to write self-explanatory code. But that concept is a bit vague, and I do not really agree with him on this. You can form your own opinions on people who disagree with pillars of wisdom like him. There are few comments in the methods in this unit because there really is nothing complicated here. The list is an object with a pointer to the first node, the first link in the chain, and everything else follows from there. It has a whole bunch of methods to add, remove and find nodes and to move from one node to another. It does not have a concept of a current node or a cursor. It's just a plain old list, and that was a deliberate design decision. The only property type value that it holds is the number of elements in the data record. This is necessary for the node constructor in order to set the length of the data array. On its own, this list is of very little use and is not actually intended to be used directly. So at the top of the chain there is the node record and the linked list. Next in line is the list runner, which contains a linked list. I didn't initially have this as a descendant of the linked list, but then I changed it to a raw object owning a list. Actually, this was a late addition to the hierarchy being inserted at the base. This element does not exist in version 4a. It was added to separate the concept of the cursor and some list methods from the dataset kind of stuff. The data list was always intended for multi-threaded access, and the design intention was to use the list runner as the list handler for each thread. That is, each thread would use its own list runner to access the list. although only one list runner can actually own the list, and the owner would normally be the list runner in the dataset, or more correctly, as the dataset. The owner will create and free the list, the others will just use it, or at least that is the design intention. Each list runner will have its own cursor and concept of where it has got to and where it is going. The idea is that while the data list object owns the linked list, the application would use one or two threads for preemptive background loading of data, and another thread for posting updates, and possibly yet another for searches with or without indexes. This is a bit like cursor cloning in the client dataset, at least conceptually, but the implementation is quite different. Obviously, this applies only to targets that allow multitasking. The list runner only declares the linked list, a cursor, and methods to handle it. The list runner methods are all simple, many just wrappers around the core list methods. The first proper dataset type object for use in forms and processes is the T-data light. It introduces the header list, the field defs equivalent, and also the endpoint list. This is intended for use in read-only situations, so only has methods to access data values, and nothing complicated or exciting. The introduction of the headers list allows the data list to know whether it should deal with a data value as a string, integer, or whatever. It also has methods to find records and to navigate the list, moving backwards and forwards. Unnecessary duplication of effort? Who knows? This class also introduces some notification events to allow the programmer to do stuff before and after. Find methods, movement methods, and some properties to access the data values. As I said a minute ago, this is the base class for actual use in forms and processes. It is intended for use in read-only situations. Intended for read-only, but that does not mean that it cannot be editable. It would be okay in any situation where the changelog and undo features are not required. The next level is the T-data list, which extends the T-data light that we have just looked at. This introduces the change list and the undo list, so represents the intended base class for editable data. Yes, these two classes could be combined, and that is something that might happen if it seems the right thing to do in future. The theory is that change lists and undo handling should not be necessary in read-only situations, and there are a lot of those. It has methods to override the previous versions to introduce the change logging. I want the undo process to be built into the dataset as a standard feature that can always be accessed. At some point I will turn the redo bits back on, but at the moment that is disabled. Here we see a simple date property setter, and after setting the values, although perhaps it should be before, it checks to see whether we're logging changes, and if we are, it logs them, and if we're using the undo system, it also registers it in the undo list. The next level is the T-index list, which, as the name suggests, introduces the ability to index the data list in memory. It adds an indexer from the light index unit and overrides some search and find methods to allow it to be done by index. It also adds some new index-based search methods, obviously intended for larger in-memory data lists. What the indexing gives is the ability to jump array style to any point in the data based on one or more values. This can make indexing an effective tool even in moderately sized data lists. Page and index sizing will be considered in the next video. The index list is the last list of the three that actually represent the data list classes. Looking here at the hierarchy, it is the second to bottom in the center column. Below it is just the data lists class, which holds lists of lists of lists and kind of represents a .NET style data set. The index list has an indexer object, which is just a list of indexes with some methods to manage them. This is a very basic class and of little interest. The indexing is page-based as a list of records. An index is also a list of index pages. It uses a bisection search approach, both at the index level to find the right page and then at the page level to find the record. It's not perfect, but works well enough. It is also still t-list based, as each page is a fixed size, although the number of pages obviously varies. The page size is not globally fixed, rather it is calculated, or can be, based on the actual or expected number of records in the data list. The t-list based version of the dataset used the index of the record, but now it holds a pointer to the actual node. The index can be based on up to 3 fields and can be unique or multi-value. Entries in a multi-value index will be ordered by record ID if it is set. The indexes were originally intended to be unique and return one value. However, they now contain duplicates if necessary and return all records for the search values. I've now made another change resulting from some testing I did, and now it can find a record and, using that as a start point, return the next n records in sequence. The index page here really just has methods to add nodes and to find nodes. The spans method indicates whether a search set should be on this page, and if the page is full, then adding a new record will cause the page to be split into 2. Scrolling down to the index, this looks quite similar. The find methods will first find the page and then ask the page to find the node. The set methods will similarly start by finding the right page and then asking the page to add the method. Using indexes creates 2 stress points in the process. Firstly, there is a large impact on the initial index creation, but there is also continuous work in editable data situations, with records being moved from one place to another in the indexes. In native apps, the indexing should be done in separate threads. I work on the assumption that it would be design error to load so much data into a web page that it needed to be indexed in the first page. Index lists are not intended for web work and could appear slow in some situations, but what do I know? That is all I want to show today. Thank you for watching. In the next video I will show the data processes in action.